Today we're going to be graphing exponential functions. Graphing exponential functions includes the transformations we reviewed multiple times already this year, shifting left, right, up, down, reflections, dilations, all of that stuff. Before we review graphing, there's some exponent rules we need to go over. We did review these rules a couple of days ago as an extra practice assignment, so hopefully you're remembering some of this. Also, I added some extra examples in my note sheet that are not on yours. It's just some basic examples. It will definitely be helpful to write them down. Of course, there's multiple rules about exponents, the product property, the power property, the quotient property, and so on. But if you just remember a couple of basic rules, you can figure them out without having to memorize anything. So if you can clearly identify what the base is and what the exponent is, the exponent tells you how many times to use the base as a factor. So here in this example, you see 8 squared. That tells you to use 8 as a factor twice. But if we come over here and we look at these two, comparing the difference between them, this top one, we have a base of 2x, and then the exponent is cubed. That's telling us to use 2x as a factor 3 times. If we use 2x as a factor 3 times, that's the same thing as saying 2 cubed times x cubed, which is 8 cubed. And then if we look at this one here, be very careful with this one. The base is just x. This is technically the same thing as 4 times x to the 6th. So the exponent is applied directly with the base. If you don't see parentheses, it is only with the term it's directly related to. So that's telling you to use only x as a factor 6 times. If you remember the base and exponent rule, you don't necessarily need to memorize any of the other properties as far as the basic power, quotient, product, and so on. But two others that are extremely important, especially for this lesson, are negative exponents and zero exponents. So for negative exponents become positive in the opposite location. So if you have a negative exponent in the numerator, it becomes a positive exponent in the denominator. And if you had a negative exponent in the denominator, it becomes positive in the numerator. I'm going to give you the opposite example. If I had 1 over a to the power of negative n, this would be a to the power of n over 1, or just a to the power of n. So this here is the opposite of the one that I already typed for you. And the last important one to memorize is 0 as an exponent. This should be the easiest one to memorize because any number raised to the power of 0 is equal to 1. It could be 1 raised to the power of 0 and the answer is 1. It could be 250 million raised to the power of 0 and your answer is still 1. So anything raised to the power of 0 is equal to 1. If we go through these 4 on your own problems, just using our basic exponents, number 1, we have 2 to the power of 0. The answer to that is 1. Number 2 is 4 raised to the power of negative 2, which is the same thing as 1 over 4 squared. Becomes positive in the denominator, which is 1 over 16. Number 3 is telling you to use the base of 6 3 times. So 6 times 6 times 6 is 216. And number 4 is telling you to use the base of 2x twice. So 2x times 2x, which is the same thing as 2 times 2, or 4, and x times x, which is x squared. All right, next we need to talk about some vocabulary. All of these vocabulary terms are terms we've already talked about this year. So let's quickly go through the formal definition of them. So starting with an asymptote, or what an asymptote is. Asymptotes are a line that a graph of a function approaches. It never touches or crosses. So the parent function of an exponential function, because that's what we're dealing with, always has an asymptote at y equals 0, and that's a horizontal asymptote. Of course, this can shift up or down with the function, but that's where the parent graph has an asymptote. When we're graphing, the y-intercept is another important factor, and this is where the graph crosses the y-axis. If you were doing this algebraically, you would set x equal to 0 and you would solve for y. For the parent function, the y-intercept is always at 1. Next, we're looking at the domain. Domain is input values, or x values, and the range is output values, or y values. But either way, if you're working with the domain and range, that means you are writing them in interval notation. Exponential functions have the general form of a times b to the power of x. As we know from the previous lesson, sometimes it's not as simple as this, but you can always simplify your equation to something of this form, which means you can certainly simplify it to identify what your value of b is. And just recall that your b value is your growth or decay factor. We're going to start by reviewing the graphs of exponential growth. Exponential growth happens when a is larger than 0 and b is larger than 1. So our first graph that we're going to look at is y equals 2 to the power of x. Now, one thing that we do have to keep in mind when we're graphing exponential functions is that the parent function changes and is specific to the problem that we're going over. So you'll see that as we go through a couple of different problems or a couple of different examples. But we're going to start with 2 to the power of x, and you can see that I set this chart up for you with x input values already designated. You could pick different ones if you want to. I do think these are the easiest, so they're the ones that I'm going to go over with you. Starting with -2. If we substitute -2 into the function, we have 2 raised to the power of -2. Well, any number raised to the power of a negative value will become positive if you write it in the opposite location. This becomes 1 over 2 to the power of positive 2. We just eliminated this negative value, which is what we want to do. This simplifies to 1 over 4. That means you're going to be graphing a point at -2, comma 1/4. If I come over to the graph, I plot that point approximately here. Next, we're testing -1. 2 to the power of -1, we can rewrite that as 1 over 2 to the power of positive 1, or 1/2. If 1/2 is our output, our ordered pair is at -1, 1/2. Two to the power of 0. Remember from the front page, anything to the power of 0 is 1. Our ordered pair will be plotted at 0, 1. Two to the power of 1 is 2. Plot the next point at 1, 2. And the last point we're testing, not the last point on the graph, but the last point we're testing is 2 to the power of 2, which is 4, giving you an ordered pair of 2, 4. Your exponential graph starts increasing very slowly and then starts to increase rapidly, and it looks something like this. Every time you graph an exponential function, your horizontal asymptote is going to start at y equals 0. It will shift up or down with the graph if there is a shift. In this case, there is no shift up or down, so this will remain at y equals 0. This is telling us that that graph never touches or crosses y equals 0. So what we call our horizontal asymptote, which is this, that happens at y equals 0. The domain of this graph, well, it continues both left and right forever, so the domain is negative to positive infinity. And lastly, the range. This graph never touches or crosses the purple line. I know my highlighter looks like it does, but it never actually touches or crosses that purple line. So it's at 1 with a round bracket to positive infinity. Never touches or, I'm sorry, it's at 0. My bad. It's at 0. It never touches or crosses that line, and it heads up forever. It heads up at a rapid speed, as you can see from our graph. It starts to get steeper and steeper. So this is your graph for y equals 2 to the power of x, and there's your important info with that. Next, let's look at an example of exponential decay. An exponential decay happens when still a is greater than 0, but now b is specifically between 0 and 1. So our example is 1/2 for our b value. Like I mentioned before, the parent function changes and is specific to the problem. In this example, our parent graph is 2 to the power of x. It's always just b to the power of x. Whatever your b value is your parent function raised to the power of x. That's it. So we need to test our 5 key points for this new parent function. We're going to start by testing -2. When I substitute -2 into this function, I have 1/2 in parentheses raised to the power of -2. When you have a fraction and an exponent, both the numerator and the denominator receive the exponent. Because we have a negative exponent in the numerator, we can replace that with a positive exponent in the denominator, and our negative exponent in the denominator will be replaced with a positive exponent in the numerator. So essentially, you're switching. This becomes 2 squared in your numerator divided by 1 squared in your denominator, which is 4 over 1, or just 4. So we can plot a point at -2, 4. Next, I have 1/2 raised to the power of -1. The same thing happens here. We have 1 raised to the power of -1 over 2 raised to the power of -1. We switch those locations. It becomes 2 over 1, which is 2. The ordered pair is at 1, 2. Sorry, -1, 2. Next, we're testing 0. Any number raised to the power of 0 is 1. Ordered pair at 0, 1. When we test an exponent of 1, any number raised to the power of 1 is itself, so 1/2 raised to the power of 1 is 1/2. Ordered pair at 1, 1/2. And our last test value is 2. 1/2 raised to the power of 2 is equal to 1 squared over 2 squared, which is 1 over 4. Ordered pair is at 2, 1/4. So this is the same, close to the same graph that we just graphed for exponential growth, except for it looks like it's flipped. It almost appears as if it's reflected. This is what exponential decay looks like. So exponential decay rapidly decreases and then slowly starts to level off. Our horizontal asymptote, the line that the graph never touches or crosses, is still at y equals 0. And for the important info, we have our horizontal asymptote at y equals 0, Our domain continues in both the left and right direction forever, so it's negative to positive infinity. And the range, it looks like it starts at 0, never touches or crosses, and heads towards positive infinity forever. There's your info. So like I mentioned, parent functions are just your b value. You might have a very complex function. You might have a lot of transformations with it. But no matter what, your parent function is just b to the power of x. So if we have a general form of y equals a times b to the power of x minus h and then plus k, put everything else aside, identify your parent function as just your b value raised to the power of x. For example, if we look at number 1, we have 3 times 2 raised to the power of x minus 1. Our b value is just 2. 2 raised to the power of x is our parent graph. It shouldn't be hard to identify. It's the number associated with the variable exponent of x, and that is it. So parent graph of number 1 is 2 raised to the power of x. That means you graph 2 to the power of x, you test your points, you graph that, and then you shift this around the coordinate plane. Number 2 is y equals 4 times 1/3 raised to the power of x plus 2 minus 1. So we have all this other info. We have this, we have something up here in the exponent, we have minus 1. None of that is important for a parent function to be identified as 1/3 raised to the power of x. You would graph 1/3 raised to the power of x, then perform the transformations on that graph. So let's take a look at transformations. So these transformations are the same transformations that we've been looking at all year. We start with our horizontal shift, which is now going to be within your exponent. So if you are subtracting a value in your exponent, then you are shifting the graph to the right. And if you are adding a value in your exponent, you are shifting the graph to the left. After you do your horizontal shift, you then move on to stretching, shrinking, and reflecting. So for stretching, shrinking, and reflecting, if you have an a value, that's going to be a stretch or a shrink. If you have a negative sign in front of the a value, that is going to be a reflection across the x-axis. And you probably won't see many of these, but if you have a negative sign, specifically with the value of x, so if you had a negative sign right here, that's telling you to reflect this function across the y-axis. Once you do your stretch, shrink, or reflection, your last step is your vertical shift. Your vertical shift is your up or down shift. If you are adding, you are shifting up. If you are subtracting, you are shifting down. It is imperative, so absolutely important, that you follow these transformations in the correct order. So in this table, you move from left to right. Also, your horizontal asymptote always starts at 0, but it shifts up or down with the graph. So a quick shortcut to your horizontal asymptote is to just understand where what your k value is. If you have a k value, that k value is going to be your horizontal asymptote. And I'll show you when we go over the few examples. To start with, we have a function, y is equal to 3 raised to the power of x minus 1. Our first step is to identify our parent function, which is 3 raised to the power of x. Once we identify the parent function, I would suggest making a table of values. Use the 5 key values that we tested on our first functions. So we'll test -2, -1, 0, 1, and 2. If you test -2, 3 raised to the power of -2 is the same thing as 1 over 3 squared. which is 1 over 9. 3 raised to the power of negative 1 is 1 over 3. 3 raised to the power of 0 is 1. 3 raised to the power of 1 is 3. And 3 raised to the power of 2 is 9. So I'm going to graph my parent function. And now that I have my parent function graphed, I'm going to indicate what my transformations are. Make sure you follow the transformations in the correct order. This example, nice and easy, we only have one transformation. Subtracting a 1 in the numerator is going to be a shift to the right 1 unit. I take my parent graph, I shift every point to the right 1 unit. The horizontal asymptote is still at 0. We did not shift this graph up or down. So I can still say that I have a horizontal asymptote at y equals 0. My domain is still negative to positive infinity. The range is going to be 0 to positive infinity. We did not shift this graph up or down, so it's still from 0 heading towards positive infinity. And then lastly, we just need to identify this y-intercept. So if you can't tell what the y-intercept is from the graph, then you substitute 0 in for x and you solve for y. If you substitute 0 in for x into the original function, you would get 3 raised to the power of negative 1. 3 raised to the power of negative 1 is 1/3. So in this example, if you were to ask to find your y-intercept, you write it as an ordered pair, x-coordinate 0, y-coordinate 1/3. You do not have to use the graph for your y-intercept. You can use the original function. In fact, usually I do. I think it's like safer to use the original function because you can clearly see what you're looking at. There's your final graph. Here's your final info. Okay, number 2. 2 times 2 raised to the power of x plus 1. 2 raised to the power of x is your parent graph. We already tested these values, but I'm going to write them again so they're right here for us to graph with. We have negative 2, our output was 1/4. Negative 1, our output was 1/2. 0, our output is 1. 1, our output is 2. 2, our output is 4. If I graph our parent function, starts off close to the asymptote, starts to rapidly increase. That's our parent graph. Now I'm going to identify the transformations. We don't have a left or right shift, so we can skip the horizontal section. We do have a value of A. This value of A tells you that you have a vertical shift. This is your first step. I'm sorry, vertical stretch. I'm saying shift, but stretch. So if you forgot from the last time we did this, a vertical stretch means to multiply the y coordinates by 2. After you do that first step, you need to take a look at your up or down shift. In this case, we have a shift up 1. This is the second step. So to perform these transformations, I'm going to come down to my parent graph. I like to look at the point right in the coordinate plane and multiply my y coordinates. but you could do it off to the side. You could do it on the table. We just made a table of values. So if you want to, you could come over here. You could multiply every point by 2. 1/4 times 2 would be 2 over 4, which simplifies to 1/2. So I can replot this point at 1/2. 1/2 times 2 simplifies to 2 over 2, which is 1. So I can replot this point at 1. 1 times 2 is 2. Right here we have a y-coordinate of 2. 2 times 2 is 4. Here we have a y-coordinate of 4. 4 times 2 is 8. So you can either do them right in the coordinate plane, or you could do it over here using your table. However you want to do that, just make sure you multiply your y-coordinates only by a value of 2. The asymptote still hasn't moved. It's still at 0 at this point. Our purple graph is our second step. And our last step is to shift our purple graph up 1 unit. So every point gets moved up 1 unit for your final answer. Now that we just shifted our graph up 1 unit, our horizontal asymptote also shifted up 1 unit. So when it was previously at 0 for every other graph that we've done, it is now at y equals 1. If the graph shifts up, so does the asymptote. Horizontal asymptote is at y equals 1. The domain is still all real numbers, negative to positive infinity. The range now starts at 1 and moves towards positive infinity. And your y-intercept. If you can't tell that your y-intercept is at 0, 3, then substitute x equals 0 back into the original function and solve for y. But I'm telling you right now that the y-intercept is at 0, 3, and I just looked right at the graph for that. You guys could do whatever you want. Here's your final answer.